So we are considering the fluid flow equations for gas dynamic flows, and previous classes we looked at general integral and differential forms of these equations. Now let us become more specific and look at a particular assumption that is very often used to understand gas dynamic flows, and it's quite useful, which is the quasi-1D assumption. So what does this quasi-1D assumption imply? Let's take for example flows in ducts or in long pipes. If you look at the distribution of the velocities, they have if you just move away from the entrance length, which is over here, which is where there is changes of the profile, but after the entrance length the velocity profile is more or less frozen into this particular shape. This is for a laminar profile, while for a turbulent case the profile will be more sharp and then having a more rounded off shape in the center. So now there can we can come up with an equivalent sort of profile or equivalent profile which has a constant velocity, or the flow property is constant across the entire cross section of the duct. So in order to do that, the principles that we use are still the same, that all conservations should be followed. So this is a the one dimensional profile having a constant velocity v. Okay. Now if you look at the shapes for the laminar profile and the turbulent profile, you see that turbulent profile more or less approximates this constant property across the duct, while for laminar profile the variation is quite significant. So this is a simplification that can be used in order to understand how the flow behaves in many different scenarios. So there are many different things that can change in a compressible flow, like you have changes in the duct area, or you could have certain heat being added to the flow, or you could have that there is a force of friction which is always present in these flows. So this quasi-1D assumption, where you say that flow variables are uniform across every cross section. So if you consider a variable duct, then across each cross section you are saying that that the flow variables like velocity, pressure and temperature are uniform, but they can change along the duct. So along, if this I consider as x direction, along x direction they can change, but across this coordinate, that is the transverse or y, or if you consider this as an axisymmetric, this can be r. So in along those coordinates the flow variables are constant. This is a particular assumption which is the quasi-1D assumption, and it is quite reasonably close to turbulent flows, because their real actual velocity profiles have similar nature, and it is a very useful tool in order to understand these different forcing due to area, friction and heat addition. So as taking this assumption, one can derive a separate set of conservation equations, and bear in mind that these quasi-1D assumption is applicable when there are only gradual changes to area, friction and so on. If sudden changes in area happen, then it is not possible to use this approach to come with reasonable estimates. So, let us take the integral form of the mass conservation equation. We are considering only steady flows, because of that this term is 0, and that is due to the unsteady term, and we have only the flux term across the control surface, that is rho v and nda, that is v dot nda, and now the velocity is considered to be uniform across the cross section. So, if I consider a cross section here A, and then the velocity profile is uniform at V. So, then this is nothing but this integration directly gives us so is density, not just velocity, density, temperature, pressure, they are considered to be uniform across the cross section. So, this will be rho v multiplied by A, that is the area of that duct or that particular cross section. So, then if we consider two such cross sections, then this statement of mass conservation implies rho 1 v 1 or rho v a is constant, or rho 1 v 1 a 1 equal to rho 2 v 2 a 2. Now, v is just a variable, is just one value, that is it is a uniform velocity here. So, given rho v a is constant, it can be written in the differential form also, d rho by rho plus dv by v plus dA by a equal to 0. This comes by just differentiating rho v a equal to 0. Okay, so if you differentiate this, you will get this form of the equation. So, in the integral form, it is rho v a is constant, and in differential form d rho by rho plus dv by v plus dA by a equal to 0. Now, when we consider conservation of momentum, there are two kinds. One, you can consider in a 1D duct, that is the area, cross sectional area of the duct does not change. So, it remains constant. So, it is A everywhere. So, the other one is that you can consider a variable area duct, which has a gradual change in area. There are slight differences in the analysis, though the principle is the same. Again, if you write the integral form of the momentum conservation and consider steady flows, then the unsteady term is 0. Then you are left with the fluxes and the control surfaces, and your generally the shear forces are neglected. So, this term is neglected, and so is the body force term. Body force term is also neglected, and mainly because the forcing is due to pressure, and so since the velocity and density have uniform profiles, this integration turns out to be rho v square. So, rho v square, and you have two sections, so 1 and 2. So, this will be rho 2 v 2 square a 2 minus rho 1 v 1 square a 1. So, which is the term that comes right here, and then coming to the pressure forces, the pressure forces have negative sign. So, this is actually minus P2 minus P1 multiplied by A, where A is remaining constant. So, this is considered over here. Now, this, if you do the rearrangement, you come to the fact, also using the fact that A1 is equal to A2, you can write P plus rho v square equal to constant. Now, this is valid for only one dimensional ducts. This integral form, P plus rho v square equal to constant for one dimensional duct. But when you come to ducts which are quasi 1D, that means there is a gradual change in area, then when you consider this momentum equation, it has to be considered carefully by considering the area change also, because now when you consider the pressure forces in the 1D case, since pressure is uniform, the integral of pressure over the lateral surface will turn out to be 0 because of the cancellation of forces, and only the pressure force along the x direction will be affecting. But in variable area ducts which have gradual changes in area, then you see that there is a component of the pressure force, that varying pressure force along the wall or along the lateral surface, that will appear along the x direction. It is we can get that particular force also. So this has to be considered a little bit more carefully. So here we have in this case a very gradually varying area with a certain divergence, say theta, and the forces, the variables are P, rho, V, A on the left hand side, and on the right hand side there is a small change in them, P plus dP, rho plus d rho, A plus dA, and so on. This force is due to gravity, body force, that is F5. Okay, so now let us consider this. So this has to be considered now. Now the integration can be performed because you are considering uniform variable. So you have on the left hand side this nothing but integral of rho v dot n dA. So this is rho v square multiplied by A, which can also be written as m dot into V, that where m dot is constant. So that is how this term comes about. M dot is V plus dV minus, that is the left hand side, which is rho A V dV. Okay. So now coming to the right hand side of the equation, these are the different force terms, that is the forces due to now all of them we are considering only along the x direction, so that has to be borne in mind. So let's the force on the left surface, the right surface, the lateral surface, viscous force, and the body force. Now pressure force on the left surface. So this is pressure force on the left surface, which is PA, P multiplied by A, so this has to be L. And while on the pressure force on the right surface is P plus dP multiplied by A plus dA. So this can be expanded and you are considering dP dA is very small, that can be neglected, it can be neglected. So if you consider that condition, then you can write this equation as PA minus PdA minus AdP. Now you have to consider the pressure on the force on the lateral surface due to variation of pressure. Now and the component that appears along the x direction. So this is the force and the component appearing, so this is theta actually. So that component appearing along the x direction is has this sin theta component. Now so the mean pressure, so the force on the lateral surface area is the mean pressure multiplied by wall area multiplied by the sine of that component, and if you do that, the mean pressure is P plus dP by 2, and if you do that, the sign component actually turns out to be dA, that is the change in area. So you get P plus dP by 2 multiplied by dA, it's mean pressure multiplied by 1. Now the viscous force is the shear stress along the wall multiplied by the perimeter area, which is you can look at these, and if this is dl, this is dl cos theta, it is along the x direction. So it is along the x direction, and you can use the definition of the frictional factor, that is, or the coefficient of friction. So there are two kinds which can be used. The way it is defined over here, this is the friction factor, which is F is 4 times by half rho v square. Okay. While this term tau wall by half rho v square is the coefficient of friction. So and thus the viscous term, if this can be considered a mean friction factor, then the viscous term is given by F rho v square by 2 and A dx by dE. Okay. And the body force is nothing but mean density multiplied by the volume and multiplied by the gravity constant, and the component that has to be considered along x direction is the cos phi term. So once that is done, then you will get g dl cos phi, which is here. Okay, this is the component along the x direction, and dl cos phi is actually dz. So you get rho a g dz. Now you can finally sum everything up. So once you sum up everything, then you are left with this equation. So and you can divide throughout by rho a v. So once you divide everything by rho a, that is this term, then you get dP by rho plus v dV plus f v square by 2 dx by dE plus g dz equal to 0. So if you neglect body and viscous forces, then what we get is dP by rho plus v dV equal to 0. This is the Euler's equation. So now we see that for a quasi-1D duct, the final equation is of this form, and when you are considering quasi-1D ducts, you have to be really careful with the analysis, and should consider the lateral forces also. Now having considered mass and momentum, now we come to the energy equation. Now when we look at this energy equation, again we are considering steady flows. So for steady flow energy equation, you have h plus v square by 2 plus gz. H is the enthalpy, and on the right hand side you have net heat added to the system and work done by the system. Okay. So now you can, this is the total energy. Total energy is h1 plus v1 square by 2 plus gz. That is, now since all parameters are constant, you get rho va, that integral, multiplied by h plus v square by 2 plus gz. This will be the integral across two surfaces, so going from 1 to 2. So this is the integral. So this is nothing but mass flow rate m dot, and this is the total energy h plus v square by 2 plus gz. That is what is written over here. m dot Et2 minus Et1 total energy is equal to q dot minus w dot. So, now this has been expanded, and you can write this in terms of enthalpy. So, this is the final equation that you get after integrating q dot plus w dot. This can be differentiated also, and this is the rate at which the heat is added and rate at which work is done, and dH plus dV square by 2 plus g dz. So, if you look at all the quasi 1D relations, you have in the integral form the mass flow rate, total mass flow rate through the system remains constant, that is rho u a equal to rho v a equal to constant. If you differentiate it, you get d rho by rho plus dv by v plus dA by a equal to 0. Now, if you consider the momentum in a 1D duct, then it is p plus rho v square equal to constant, while in a quasi 1D duct, that is the area is changing very gradually. The relevant equation is dp by rho plus v dv plus this is the friction term and this is the body force term, and if these are negligible, dp by rho plus v dv equal to 0. For a quasi 1D duct, the energy conservation is the total change of energy is related to heat added and work done, and it can be written even in the differential form. So, now having considered this quasi 1D relations, is a very useful assumption to make that the flow variables are constant across every cross section, and then we can see how if there is a variation of area or if there is a heat addition or if there is friction, how it affects the various flow parameters, and that is what we would be doing in further classes. Immediately in the next class we will apply the 1D relations to look at how to see the speed of sound, how we can estimate the speed of sound. It will be a sort of application of these material that we have just covered. At the same time, we will also get to know how we can estimate speed of sound.